Well, here we are again, another Monday. So, of course, the semester is winding down a little bit here. So what I've done here is on Moodle, I put not one, but two problem sets to give you some practice in probability theory. And I'm showing them right here. And they're called Chapter 11 problems number 1 and 2. So I'd like to go over those on Thursday. And it's just what we just got through doing in Chapter 11. And this is good practice for the final exam, of course, which is only based on 11 and 12. It is not comprehensive. All right, just keep that in mind. So it should be very well, at least, manageable. If it had been comprehensive, it would have been very long and massive. So instead, we just have those last two chapters. All right, anyway, so in the meantime, what we're going to do is go back to Chapter 12, which we really just barely started the other day. And of course, Chapter 12 is our discussion about statistics. So let's get back to that right now. And of course, with this chapter I mentioned before, there's going to be a lot of calculations. All right. And so let's get to it. So remember, with statistics, we started out by discussing the differences between a population and a sample. And all of the analysis that we'll be using in this chapter will be applied to either populations or samples, although most of the time we'll be looking at samples. All right, it's very unusual, as a matter of fact, that we have enough information about the entire population to analyze it correctly. So instead, we usually resort to samples. So just as a quick review, a population is a collection of measurements or outcomes of interest. Now, of course, normally we think of the word population as being a collection of people, but here we're really more interested in characteristics of those people, like, for example, their ages or their incomes, or how far they drive to work every day, numbers like that. So a population is typically very large, and it could be very difficult to analyze every element of a population. So most of the time, we don't actually use the entire population. Instead, we draw samples from that population that we hope reflect the actual properties of that population. So that saves us a lot of time and effort, and maybe a lot of money too, for that matter. So a lot of statistics is based on our drawing of samples from a population and trying to draw conclusions about the properties of that population. Now, of course, sampling has to be done very carefully, because if it does not truly reflect the underlying population, then the results that we get will be meaningless. All right, so that's a big deal. Now, sampling can be done in many, many different ways. All right, the technique that we choose for our sampling typically depends on what discipline we're working in. For example, economists would use a very different technique for sampling than, let's say, psychologists or biologists, because the information that they are working with is very different, and they are maybe looking for different types of information. So for our purposes, we'll keep it simple. We're basically going to assume that when we draw a sample, all we're doing is picking randomly, potentially from every member of the population, so that every member of the population has an equal chance of being chosen. So it's like, imagine if I randomly sampled from this class and I just assigned everybody a number, and then I just randomly pick numbers, and those numbers determine who gets picked for my sample. So that's the type of sample that we'll be focusing on here. And by the way, that is referred to as a random sample because of the way the elements are chosen. Now, we mentioned this example last time. If the government is interested in analyzing how, if the population is aging in the United States, and there's a lot of good reasons for doing this, because a lot of their expenditures depend on the age of the population. For example, Social Security, Medicare, Medicaid, all the rest of them, a lot of that spending is based on people above a certain age. And so the longer people live, of course, the more they're going to have to spend on those programs. So it would be helpful if they know what the average age is of the Americans who live here, and And also it's helpful to know if it's increasing, which it almost certainly is. We know that people keep living longer and longer and longer because medicine keeps improving, and also because people are more conscious about how important it is to live a healthy lifestyle. So there's a pretty good chance that the average age is going up, even in just the last 20 years, which is good. But from the government's perspective, that also means they have to make sure that they don't run out of money for these different programs. Okay, so if they find that the age is going up, they may have to figure out other alternative ways of financing Social Security and Medicare and all the rest of them. So now the problem, though, is that even though they could, in principle, take a look at every single American, there's so many of them, over 330 million, that this could take an incredibly long time to do. So what can they do instead? Well, there's no real need to look at the entire population. They can get very accurate results by looking at a sample, as long as that sample is chosen well. So, for example, imagine if they randomly choose 100,000 people scattered across the entire country. If they've chosen these people carefully, then the average age of the people in the sample should be very close to the average age of the entire country. It won't be perfect, but it should be very close enough so that they can decide what to do about financing Social Security and Medicare and all the rest of them. Okay, so we don't expect perfection, but we want it to be very, very close. All right, so for example, if the average age is 29, we don't want the sample to tell us that it's 54. That would be a disaster. Okay, so instead, we want to make sure that this is close, and the way we can ensure that is by randomly choosing the sample, as opposed to, let's say, only picking people who are already above a certain age, or, there, in the past, sampling mistakes have been made in many cases. And in fact, I'm going to show you in a few minutes an example of how not to do marketing research, but we'll get to that in a few minutes. Again, as long as the sample is chosen properly, we shouldn't have a problem. Now, by the way, there do exist marketing firms whose only job is to do these types of samples and come up with information that is needed by corporations who are trying to sell products. Like, for example, Coca-Cola, as we're going to see in the next example. Suppose they've developed a new flavor, pumpkin Coke. Now, they don't know if people want to buy pumpkin Coke or not. They don't want to spend a lot of money marketing a product that nobody likes. So what can they do? Rather than take a chance and just put it out in the market, they can hire a marketing firm and say, listen, find out what proportion of the population actually likes this flavor. That would be, of course, much cheaper than trying to contact everybody in the country and finding out what their opinion is about the pumpkin Coke. So the marketing firm, being specialists in this area, know how to choose people carefully so that the opinions of the people in the samples that they draw should reflect the overall population very closely. So they'll do things like offer free samples to shoppers in the supermarket. They'll stand around in the mall and give out certificates. They give you like free cans of pumpkin Coke. There's all kinds of strategies that they can use. So as long as the people that they survey are accurately reflecting the entire population, then they should be able to tell Coke more or less what proportion of the people they surveyed, if they like the flavor or not. And then Coke has to decide what proportion is high enough that they can afford to bring it to market. For example, it might turn out that they can only make money if the proportion is at least 30%, and then that's what they'll be looking for in the results. So I sneaked in here an example based on the Coca-Cola Company, a disaster that faced them about 40 years ago now. And so I called this section, How Not to Conduct Market Research. Okay, so this is a disaster that befell the Coca-Cola Company in the early 80s. And it isn't directly related to the sampling that they did, but the way they carried out the research itself. But I think you'll find this to be very interesting. And it shows you how easily things can go horribly wrong when we try to do marketing research based on samples of people. It doesn't always work out well, okay? And so what happened here was that in the early 80s, The Coca-Cola company was worried, of course, that they were losing market share to PepsiCo, their main competitor. Now, keep in mind that at this point in time, they didn't have nearly as many flavors out there as they do now. It was just Coke and Diet Coke. That was pretty much it. Now, they also had brands that they had purchased themselves. For example, I think at that time they owned Dr. Pepper, for example. And so, they had flavors available because they bought out quite a few of their competitors. But the basic Coca-Cola line consisted almost exclusively of Coca-Cola and Diet Coke, and that's all they had. Same thing was really true with PepsiCo. They had Pepsi and they had Diet Pepsi, and that's pretty much it. Now, the problem is that Coca-Cola was worried about losing market share to PepsiCo. They were considered, and particularly they were worried that Coke was perceived as not being sweet enough for the general public. They were worried that PepsiCo was taking their market share because people preferred Pepsi, which is slightly sweeter than Coke, slightly being the key word there. Now, so what they did was they had their researchers get together and create a new flavor, which they called New Coke, which was slightly sweeter, which they felt would compete very well with Pepsi. So what went wrong? What horrible problems did they run into? Well, I mean, as I mentioned before, naturally enough, before they brought it out to the market, they decided to do some research. They would have people come in and try the new Coke and compare it with the old Coke and see which one they like better. And so typically what happens is they have people sitting there and they have a cup in front of them, one of each, traditional Coke and new Coke, and they're asked, which one do you like better, before they know which one is which. So the results look promising for the new Coke. A lot of people, the majority said, yeah, we like this new Coke. Not knowing what it was, of course. All they knew is that there were two flavors in those two cups, and the ones that most of them picked turned out to be the new Coke. Okay, they had no idea what else was going on here. All they were asked to do was, do you like this flavor or that flavor? Which one do you like better? And so most of them did say new Coke. Well, Coca-Cola thought that was fantastic news. Now all they have to do is bring out the new Coke, and they should have a leg up on PepsiCo. So what went wrong? Well, here's what happened. Without telling anybody what their plans were, what they did was, rather than adding new Coke to their existing product lines, they went out and they replaced the traditional Coke with the new Coke. In other words, they pulled all the traditional Coke off the shelves, and all of a sudden, it only became possible to buy new Coke. Now, the people who were tested and asked about which flavor they preferred were not told that this is what Coke had in mind. All they said was, yes, we like this new Coke. We like it. Maybe a little better than the original Coke. They were not told that the plan was to replace the old Coke with a new one. So once it became clear that that's what was going on, there was a huge backlash. People were really angry with the company. They felt like they'd been deceived. And so eventually what Coca-Cola had to do, because their sales started plummeting, what they did was, in a way, try to cover their behinds. And what they did was they reintroduced the original Coca-Cola with a new label called Coke Classic, so that they were then selling both products at the same time. But the bad publicity was so bad that they lost a lot of money. And a lot of people were fired, as you can imagine. And eventually, about 7 years later, they pulled new Coke from the shelves altogether. And then the so-called Coke Classic was relabeled once again to its proper name, which is just Coke. Okay, so when you buy a can of Coke now, it's the same one that they always made. You no longer will be able to go to a store and find something called Coke Classic, because it's the same thing. So the bottom line is that they not only lost all this money, but then apparently PepsiCo made fun of them in their ads. And so let's just say that this was a disaster. I mean, once in a generation disaster that you run into in marketing. It's it's kind of one of those cases that is analyzed in business schools even to this day as an exact example of what not to do. Okay, so marketing wise, the company screwed up royally. I don't think the statistical part was really the problem. It's not that they chose the wrong people or something along those lines. It's just that the whole setup was a disaster. And it just shows that using sample data requires us to be careful, not just with the way it's gathered, but the way that it is presented and the way it is interpreted. So it just goes to show that sometimes sampling doesn't necessarily lead to the best results. But if they'd known what they're, I mean, really, any statistician could have told them that they were making a terrible mistake by doing it this way. All right. Well, anyway, now, of course, there have been many other disasters as well, but this is just one that I thought made sense for this chapter. Anyway, so what else have we done in this section? So here's what we're going to start with today. This is the first new thing today. We're going to introduce what are called measures of central tendency, which are numerical measures that help us understand the key properties of either a sample or a population. So in other words, it's really difficult to analyze a group of data. We typically like to take some or calculate some measures that help us understand certain key properties. Otherwise, it's, we just have a bunch of numbers. And so we're trying to make sense out of them. And one of the ways to make sense is to create these so-called measures of central tendency. Now, there are three of them that we want to consider today. And most likely you've heard of at least one of them. Maybe all three of them. So what are they? Well, let me show you the list. Now, the first one, actually, I've written in parentheses the alternative name for it. So you can see that mean, median, and mode are the three measures of central tendency that we will be defining today. And I just wanted to note here in parentheses that the word mean is simply another name for average. Okay, average and mean are the same thing. Actually, this happens quite a bit in statistics. There are quite a few terms where there are multiple names that represent the same thing. This is one of those cases. Mean and average represent the same idea. Then we also have median and we have mode. Now, everybody knows intuitively how to calculate an average. Okay, that I'm sure of that, but you might not know, there are certain details that we have to know. And there's also multiple ways of calculating an average. So in other words, the way that we all know is valid, but for certain situations, there are other alternative types of means or averages that make more sense. So we'll be looking at least one of those today. The median and the mode are not used quite as frequently as the mean, but they're awfully important under certain conditions. And so we need to understand how they work. All right, now, before we go any further, for these measures, in most cases, we're going to introduce them with formulas. And the formulas themselves may look very, very scary when you first see them. But once we've worked with them a little bit, you'll see that they're really not very scary at all. But it takes a little getting used to. All right, so also I want to point out that as we go along, whenever we have a formula for a sample, we need to have a corresponding formula for a population. Both of them need their own individual sets of formulas. So we're going to start by introducing the formula for calculating the mean of a sample. All right, we're using the sample because that's the one that we're most likely to use in practice. Like I said before, we don't normally use the populations because they're usually very large. So we'll start by introducing the mean of a sample, which we'll call simply the sample mean. All right, so like I said, be prepared to be shocked when you see this formula, but then be prepared to see that it's really not that bad. All right, here we go. All right, don't say I didn't warn you. Oh no. All right, so I've been writing on this slide, as you can tell, but the formula is X bar equals all of this on the numerator and this n on the denominator. Actually, let me get these out of there for the time being so you can really see the formula properly. This is my formula. Oh, I can highlight it and everything. Look at that. No, I don't want anything to block your view of it. So this is the formula right here. So the question is, what do all these pieces mean? All right, well, we'll start with the X bar. In the upper left-hand corner, you see that little line on top is referred to as a bar in statistics. So that becomes X bar. All right, X bar. And so whenever you see that bar in statistics, oh, that's not what I wanted to do. X bar, the bar means that we're calculating some kind of an average. That's all it means. It's a symbol that's widely used in statistics to represent an average. Now, if you notice in the denominator, we have the letter n, lowercase n. This is the sample size, or in other words, how many elements are in your sample. All right. Now, what else do we need to explain? Oh, here we go. How about this x with a little I? That I is known as an index, and it is a number, which you'll see here, can range from 1 all the way up to n, the sample size. What is it for? What does that mean? Well, each xi is a different element in the sample. The index is used to keep track of which one is which you'll see in a couple of minutes when we do some examples. So these x's are themselves simply elements of my sample. And I've saved the scariest part for last. What is this thing? Well, if you look over here on the left, this symbol is actually a Greek letter. It is the uppercase sigma in the Greek alphabet. And sigma corresponds to S in the Roman alphabet. It has a very, very specific meaning. It is actually a mathematical operator. But what does it mean? Let's find out. Okay, let me give you a minute to catch up, and we're going to introduce sigma and find out what that's all about. All right, so once that mystery has been cleared up, it should be very clear what we're doing in this formula. All right, here we go. So, I want here the next example. I just want to illustrate what the index actually means. So imagine the following situation. You find yourself in Minneapolis and you're visiting the Mall of America, which is at the moment the largest mall in the country. And this mall is so gigantic that it actually has 3 Starbucks in it. Okay, it's that big. 3 of them because it's so big. It's almost like a small city. And so what we're going to do is use it for the following purpose. We're going to use each of those X's to represent the price of a cup of coffee at those 3 Starbucks. So therefore, X1, now imagine you're walking in the door, the first Starbucks that you see, we'll call it the first Starbucks. And it turns out that they're charging $2 a cup. All right. Then as you keep walking through this enormous mall, thinking that it's going to go on for hundreds of miles, but not really, the second Starbucks that you run into is charging $2.10. And then the third Starbucks, and the way in the back of the mall, is charging $1.95. So I've got 3 elements in my sample. X1 represents the first Starbucks price, X2 is the second Starbucks price, and X3 is the third Starbucks price. So the index tells me which store this information came from. So for every sample that we'll be using, we'll do the same thing. We need to keep track of those elements, and so we'll do that with an index. Okay, so instead of using different letters for each one, we'll have the same letter, which is X, but each one will have a different index. All right, so that's what that's all about. Now, by the way, if you're interested, if malls are your thing, and if you live near Philadelphia, I don't know if anyone here lives near Philadelphia. The second largest mall in the country is in the outskirts of Philadelphia in a town called King of Prussia. And it's just a little south of Philly. And so if you love malls and you want to see what a gigantic mall really looks like, you can go visit very easily, much more easily than Minneapolis, the King of Prussia Mall. All right, now this summation, this thing, the sigma, what is this all about? This sigma is a mathematical operator, which we will call from now on the summation operator. That means we're going to add something up. In fact, based on the way we've listed this thing, that's telling me in a very compact way, I'm going to add up all the elements in my sample. All right, so in other words, it's shorthand notation that says, listen, for all the elements you have in your sample, just add them up. And that's why it's called the summation operator. All right. So with that being set up, now let me just show you. Now the summation operator is actually a little bit more complex than it appears at first glance. So given, let's say we had the following elements in a sample. Those are the 5. Now imagine that these are temperatures in Celsius. And where did we get these? We went outside our house on each of the first 5 days of January, and we recorded these 5 temperatures. So we've got 5 of them, one for Monday, Tuesday, Wednesday, Thursday, and Friday. And so we'd like to know what was the average temperature during those 5 days. How would we do that? Well, intuitively, I think everybody knows that you would just add them up and divide by 5, but we want to approach this in a more formal way. So we'll start by using the summation operator or applying it to this data. So the summation operator says, all right, here's what you're actually doing. You're adding up all the elements. Now in our case, there's 5 of them. So you could write this as I equals 1 to 5. And you're just adding up all 5 of your elements. And that's what we get down here. This one in the middle is the general approach. This shows you that whatever n is, we're adding up all n elements. In the denominator, though, since we only have 5 in this case, we're just adding them up. And it turns out that they're equal to 10. That sum is 10. All right, now, what else do we have to do to calculate the mean of this sample? Let's find out. Well, we know already that the sum by itself isn't what we're looking for. We're looking for the average. So this is where you would then divide by n, which is the size of the sample, or in our case, 5. But before we do that, I want to take a step back and show you some more important details about this summation operator. Then we'll calculate our sample mean. Okay, now, we can extend the summation operator to other cases. And we're going to do this now because we will need these cases for our later formulas in this chapter. So we're not just doing this for the fun of it, although it certainly is fun. So for example, by the way, I just wanted to point out on the top here, some books do not include the I equals 1 to n, and they just write it like this on the right. It means the same thing. Okay, so I'll try to always include the index on the summation operator, but it's not absolutely necessary if it's clear what data you have to work with. But anyway, look at what happened here. All of a sudden, I've got the summation of not xi, but xi squared. Oh, are we allowed to do that? Yes, we are. But what does that tell us to do? It means we have to go through each element and square them before they're added up. Okay, so this is different. It's the sum of the squared elements instead of the sum of the original elements. So look what we have to do here. And remember, we had x1 is 2, x2 is -1. In fact, let me write these up here again. Just for reference. And what have we done? We've squared them all up, and then we were able to add them. So in other words, we have 2 squared is 4, -1 squared is 1, 3 squared is 9, 5 squared is 25, and 1 squared is 1. And when you add those up, you get 40. Okay. When we added them up directly, we got 10. When we squared them before adding them, we ended up with 40. Man, this summation operator is powerful, isn't it? There's so many different things it can do. Now let's look at a related but different example. The difference is very subtle at first when you look at it. So let me show that to you next. Give you a minute to catch up. So what about this case? Oh, something's different now. If you notice this one, I've got parentheses around the summation operator and then it gets squared. Here, that didn't happen, did it? No. So how do we interpret this case? This one tells me that I add up all the numbers first and only at the end do I square the result. Okay, so instead of squaring them and then adding them, I add them and then I square them. So that's how this one is different. Now, as a result, you'll see that when I do that, I add up all the individual elements to get 10 squared, which is 100. With the last slide, it was 40. So you can see they're two very different situations, even though they look very similar. Now, there's one more case we want to look at. And again, only because we're going to need it later on. Not because, it's fun to do these, although it is. We don't want to spend time on something that's not absolutely necessary either. So we're going to look at one final case of how this summation operator can be applied. And this one requires two things to be done before we add everything up. So there's two steps going on before we add anything. What are we going to do next? All right, let's find out. So first of all, I want to point out that this K that you see here in this formula is a constant. It could be 3, it could be 7, it could be 52, it could be anything. So, wow, for each element, you have to do two things. You subtract K, square the result, and only then do you add up the results. All right, so there's a lot going on here, isn't there? Yes. All right, so let's look at an example. We'll take the sample we had earlier and we'll do the following. Okay, so I've repeated the sample data that we had before. And what I want to do is in each case subtract 3, square the results, and then add them up. So I did it in several stages here. First, I did the subtractions. Then I did this. Then I actually evaluated the subtractions. And then I squared them up. And then finally, at the end, they were added up to give 25. So make sure that you can get the same number with your calculator. Otherwise, well, we'll have a problem later on. All right, so once you're done with this, we're going to go back and actually calculate the sample mean of our original 5 elements. All right, so let's take a look. So we'll bring all their information back together and revisit the original formula that we were looking at. And so we've got the sum of the x's, as we saw up here, equals 10. We divide by the sample size of 5, and we end up with our sample mean of 2. So this is what you would normally do anyway, but now we've done this in a very formal way so that we can apply this to any other situation we might encounter. So the average is just the sum of the 5 temperatures divided by the number of temperatures, which adds up or gives us an average of 2. And all sample means are calculated in the same way. So this formula on the left, which looked so scary 10 minutes ago, is actually not so bad, is it? No, it's even kind of simple. Oh, there you go. So now the summation operator is very straightforward, as you can see. And it's very useful because it can provide us a lot of information in a very compact way. And it can express a lot of steps that you need to take to come up with a result. All right. Now that that's done, what I'm going to introduce to you is the equivalent. Oh, no, I've got another example here. All right, good. We'll get one more example under our belts, and then we'll go on to something slightly different. Now, here's a case where a student has taken 4 exams during a semester. The scores were 80, 90, 92, and 99. What is the student's average? So you can treat those as X1, 2, 3, and 4. And you can use our formula to come up with a semester average. Now, notice here, though, that we're assuming that in this class, all the tests are weighted equally. In other words, you don't always have that. But for our purposes, let's assume for simplicity that the average at the end of the semester is simply what we've been seeing here, the sample mean, in which we are just adding the 4 of them up and dividing by 4. All right, so how would that work? All right. Let's find out. So I've written the data up again here just for reference. This is the formula. So the numerator means you add up the 4 elements, in this case, the 4 exams. You add them together and you get 361. And then in the denominator, you of course have 4 because there's 4 elements. So that works out to an average of, as you can see, 90.25. That's the average for the semester. All right, now I did mention before that for every sample formula, we're going to need an equivalent population formula. In the next, so what we're going to do next, we don't need a separate example of it because the steps are the same, but the notation is slightly different. So when you look at it, you'll see that it looks different because it is meant to represent a population mean compared to a sample mean. So, all right, let's take a look. Oh, now there's two, I wrote the other formula again here so you can see it. There's two main differences between the population formula and the sample formula. The most obvious one that jumps off the page at you is this one. That is the Greek, as you can see on the top, that is the Greek letter mu, and it is used to represent the mean of a population. And they chose that apparently because this is the equivalent of the M in the Roman alphabet. So M for mean, it makes sense. The other difference is that we're using capital N's instead of lowercase n's to represent the size of the population. So we know which is which. So from now on, lowercase n is sample size, capital N is population size. The reason why we need to do this is because in some formulas, both of these will appear in the same formula, and we have to have a way of telling them apart. Okay, so that's why this is being done. The Greek part, there's a convention in statistics where population measures will be expressed with Greek letters and sample measures will be represented with Roman letters. So that's why we have mu for the population mean and x bar for the sample mean. Because remember, Greek letters go with populations, Roman letters go with samples. All right, now we're going to move into an interesting, well, remember I mentioned earlier that there are different kinds of averages that we could potentially describe. The one that we all know from, whatever grade level we were in has us take all the elements that we have, sample our population, we add them up, we divide by the number of elements that we have. So, but there are several alternative approaches to using this mean that depend on what circumstances we're facing. So I'm about to introduce to you an alternative version of the average that is used for very special cases. And so it's called a weighted average. And you may have heard that terminology before. And we typically use this when some observations in the sample or population occur more frequently than others. It's meant to save us some time, but for certain situations, this is the only option that we really have. So what I'm going to do is introduce you to this new formula, and it's going to look scary. But you'll see after a few minutes that it's not scary at all, especially now that we really understand the how the summation operator works. All right, here we go. The sample mean, the sample weighted average, I should say, looks like this. Okay, so yes, it looks frightening. But if you look at it carefully, you'll notice in the numerator, oh, before we go any further, I just want to mention that with a weighted average, we're assuming that each element xi has associated with it a weight, which we'll call wi. So we'll explain what the weights mean in a few minutes. But the important detail is that each element in our sample now has associated with it something called a weight, which basically refers to its relative importance in that sample. Okay, and again, I'll explain that when we go along. The weight represents the proportion or the importance of that element in the sample. So if you look at the numerator of the scary formula, it's telling us that for each x, we're going to multiply it by its own weight. And when we're done doing that, we're going to add up all the results. In the denominator, all we're doing is adding up the weights. So the denominator is easy. The numerator is a little tricky. So we could actually rewrite this slightly. And in fact, maybe we will. I'll give you a minute to catch up. All right, so what I'm going to do is just show you an alternative way of looking at this. Okay, so I just wanted to write it out for you more formally so you can see that the numerator means go through all the x's, multiply by their weights, and add them up. In the denominator, you're just adding up the weights. Okay. Now, the next thing we're going to do is see the equivalent version for population. So the only slight changes will be the Greek letters and the capital N. So let me just show that to you real fast. All right, so on the left, we have the population version. And again, you'll notice we have the Greek letter mu, and we have the population size, which is N. On the right-hand side, we have the original formula, X bar, because it's a sample mean, and lowercase n, because it's a sample. All right, so now we're going to do an example. Suppose that a lottery, a small lottery, okay, provides a single grand prize of $1,000, 10 prizes of 500 each, and then 100 prizes of $10 each. What would be the average prize received by a lottery winner? Okay, so if you win this lottery, on average, how much are you actually winning? Now, the reason why we're going to use a weighted average in this case is because the number of prizes is not the same. Okay, we have different numbers of $1,000 prizes, $500 prizes, and $10 prizes. Therefore, it would be a terrible mistake to simply add up the 3 prizes and divide by 3. Okay, when I say terrible, I mean terrible, because you would get a number that's not right. Okay, instead, we have to take into account the fact that there are many more $100 $10 prizes than $1,000 prizes. So that means this is a job for the weighted average formula. Now, since there's only 3 prizes, we can think of this as a population, the 3 prizes, and we'll use the population version of this formula. And so, oh, by the way, I just want to point out that in a case like this, the prizes are the actual X's. The weights are the number of prizes in each category. Okay, that's important. If you got that backwards, you cannot possibly get the right answer. So think of the prizes as the X's, or the sample elements, or in this case, population elements. The weights are the frequencies with which we observe these prizes. 1 for the $1,000 prize, 10 for the $500 prize, and finally 100 for the $10 prize. Once we've got that straight, then all we have to do is plug these numbers into our formula. All right, so remember, you have to be careful here. Just think in terms of the weights as frequencies. How often does this happen? How often do you observe X1, X2, and X3? All right, now, once you've got, like I said, once you got that straight, you can easily plug in these numbers and you'll have your answer. All right, let's check this out. And by the way, you probably should take out your calculator and make sure that you can reproduce these results. All right, so here's the formula down here. Now I've labeled it. You can see which are the W, which is W1, X1, W2, X2, W3, X3. Remember, we're multiplying the weights by the X's before adding them up in the numerator. In the denominator, we're simply adding up the weights. You can see that on the top there, the sum in the numerator, we actually end up with 7,000. In the denominator, we end up with 111. And that gives us an average prize of approximately $63.06. So you can see that not only is this the way to go, but it would have taken a long time to do it with the traditional approach, because we would have had 100 tens, 10 500s, and a single thousand in the numerator. And that would have taken a long time to add up. So this approach can sometimes save us a lot of time. All right. So, by the way, interesting to note that 6306 is not one of the prizes. The average is different than the actual prizes. And also another thing to pay attention to here is this. You notice how this number is very close to, much closer to the $10 prize than the $1,000 prize. And that's because there's so many more $10 prizes. Now, the next example is something that you're all very, very familiar with, and that is GPAs. GPAs are also weighted averages. And that's because every class doesn't have the same number of credits, typically. Most schools have some 3-credit classes and some 4-credit classes. If you're taking a lab science class of some kind, it could be worth more than that. Like, biology with lab, that kind of thing. So imagine the following situation. I've put together a fictional transcript from a student, and I'm showing the classes that this person took, the letter grades, the numerical equivalents, and the credits, and we're going to use this information to come up with their GPA for the semester. All right, so imagine this is you. You signed up for these 4 classes. Those are your grades. In the middle, we have the equivalent values. For example, a B is worth 3.0 points. A C plus is worth 2.3. A minus is 3.7. And A is a 4. And then on the far right, we have the number of credits. 4 for pre-calc and physics, because they're math and science courses. 3 for the social science courses, like English and history. That's pretty normal. I don't know, every school is different. I don't know if this is how it's done at Purchase, but let's just say that this is how it works here. What we want to know is, what is the student's GPA for the semester? It looks good, but we want to know exactly what it is. So I've expanded the table in the next slide to show you how we could approach this as a weighted average. It turns out that the credits will be the weights. The numerical grades will be the X's. The letters, we can't do anything with the letters. You can't combine them algebraically. It's the numbers that we'll need for the GPA. And of course, the name of the class doesn't tell us anything. I mean, it doesn't help us calculate the mean. So on the next table, I've added 2 new columns to show that calculus is the first class, English is the second, history is the third, physics is the fourth. So I have my 4 X's here. And these are the weights, and the weights are equal to the number of credits. Now, I'm going to treat this selection of grades as a population for this semester. This is the entire set of my grades. So I'm going to use my population weighted average formula here. And here it is. Now, it would be nice if I could squeeze all this onto one single slide. I don't think so. That's a pretty big table. Let me see what I can do. Ooh, maybe I can do it. I'm impressed with myself. I fit them both on there. Now, this is nice, so you can see what's going on here. So the first grade, my weight is 4 for pre-calculus, and 3 is my grade. For English, my weight is 3 credits. I got a 2.3. For history of Western civilization, I have 3 credits and a grade of 3.7. And then finally for physics, I've got both credits for grade 4. If you multiply those together and add them up, you'll get 46. The total number of credits is 14. And so my GPA is officially 3.29. All right, so now you know how they do this. When you look at your transcript at the end of the semester, you know what they've done, what's going on behind the scenes. Now, if all the credits were the same, you wouldn't have to go through all this trouble. You could literally just add these grades up and divide by 4, but that's often not the case. So this is the normal procedure. And again, the purpose of this is just that each grade doesn't count the same. It depends on the number of credits. So this to me is the classic example of when you really do need a weighted average. All right. Now we're moving on to the second measure of central tendency that I mentioned. Let me just go back and remind you that there were three: the mean, the median, and the mode. Okay, so we're done with mean. We're not going to get to mode today, but we'll look at median, or I don't think we will. The median is what's coming next. Now, the median is a little bit different. And most of the time, the mean is the preferred measure to the median, but there are certain cases where the median is actually a better choice. So we normally use it or reserve it for those cases. So first of all, what is the median? It's a number that basically divides our sample in half. Whatever that number is, half the elements in our sample or population are less than the median, and half are greater than the median. It's just that simple. It's the dividing line between the bottom half and the top half. Now, you've probably heard this word before, but you may not have known what it meant. The median, halfway, the halfway point. And by the way, for any given sample or population, there's no guarantee that the mean and the median will equal each other. In fact, they're usually different, although not always. Now, let me show you a couple of simple intuitive examples. Let's say that you were told that the median age of all Americans is 28. That means half the country is younger than 28 and half is older than 28. That doesn't mean it's the average, but it does mean it's the halfway point. Half are below, half are above. How about this one? How about a score in an exam? Suppose the median is 82. Half the class got less than 82 and half got better than 82. All right. That's all that it means. It's pretty straightforward, but the calculation of it is a little bit trickier because there's one extra step that we did not have to do with our mean, with our means. And what is that extra step? All right, well, let's go back to the sample that we had earlier with the temperatures. So just as a quick reminder, here they are. Before we calculate a median, what we have to do is sort them out. All right, we have to sort them from the lowest to the highest values in order to do this properly. Okay, so if we do that here, we'll end up with -1, 1, 2, 3, and 5. Okay, now where's the median? Well, here we have an odd number of values. So the median is defined to be the value in the middle. What would that be? In this case, that would be 2. 2 values or elements are less than 2 and 2 are greater than 2. So 2 is the median of this sample. That's all there is to it. So it's pretty simple, except for one thing. This is the easy case. There's a harder case that we have to contend with. What happens if we have an even number of values? Oh no, now there won't be a value right smack in the middle. We'll have to try something different. So why don't we take a look? Well, and by the way, I'll give you a spoiler here. You're going to take the average of the 2 in the middle. All right, so it's kind of a compromise, but it works. So for example, let's look at another sample that has 6 elements instead of 5. All right, so there, well, here they are. Again, they could be temperatures in Celsius in January. Let's just say that that's what they are. So there's 6 this time. Now, what do we do first? Whenever we calculate a median, the first step is always to sort the data from low to high. All right, let's see what that looks like. Okay, 0, 1, 2, 3, 4, and 6 is our sorted data. If you notice, though, there's no value in the center, there's 2 of them. And so we have to average those 2 out, and when we do, we get 2.5. So we will define 2.5 as the median of this sample because half the values are below 2.5 and half are above. So there's 2 cases that we have to concern ourselves with: odd number of values, even number of values. In both cases, the final result is the number that divides the data in half. All right, so I think we get the idea. Now, there's 2 observations that we want to make here. When we're thinking about the mean and the median, first of all, if you noticed, there's no formula. No formula. Instead, we followed a set of steps, which were sort the data and find the value in the middle. That's all that we did. There's no formula that would explain that properly, so we just follow these steps. Okay, that's our first observation. No formula, just a procedure. Observation number 2 is that the sample median and the population median are calculated in exactly the same way. There's no formula. We just do the exact same steps. We sort the data and we find the value in the middle. So we don't really have to worry about whether the data are a sample or a population. They're both treated in the same way. All right, so now what we would like to do is briefly discuss when we would use the median and when would we use the mean. Both of them are measures of central tendency. Neither one is a better choice, but under some conditions, one of them is a better choice than the other. So what exactly is this all about? In order to understand this, we have to introduce the concept of an outlier. So the bottom line here is that these mysterious outliers, which we'll explain in a minute, will affect our mean, but not our median. So now, what exactly is an outlier? These are numbers or elements of a sample or a population that are either much smaller or much larger than the rest of the data. Outliers. Okay, so let me show you a few quick examples of what outlier. You can think of these in the following way. Examples of outliers. All right, suppose that we had the following scenario. Suppose that we have a class of people with average heights and one basketball player. All right, so you got a regular group of people, just average height, and all of a sudden there's that one basketball player in the room. The height of the basketball player could be thought of as an outlier because he is so much taller than everyone else. All right. So in a case like that, you got, the heights are like 5'4", 5'6", 5'8", 5 foot whatever, and all of a sudden there's somebody in the room who's 7'2", and he's on the basketball team. Well, that height could be thought of as an outlier. It's much larger than the other observations in your sample or population. Well, here's another one that I thought of. Now, by the way, I don't know if you're aware of this or not, but at SUNY Purchase, they have this program. And what you can do is if you're retired, you can actually come to Purchase and take classes and pay really trivial amounts of money to take those classes. It's almost free. They want to encourage people to come back to school. I mean, imagine yourself working your whole life as an accountant, and one day you say, I wish I had taken some art classes. Well, there's SUNY Purchase right up the street. Why don't I sign up for some art classes at SUNY Purchase? And they'll charge me very, very little money. In fact, you may have had retired people in your classes because of this. They don't normally show up. I've had a few. They don't normally show up for math classes, of course. I mean, when you're retired, is that the time to take math classes? No. You want to take classes that are fun when you're retired, okay? Things you always wished you'd had time for, like art and music and all the rest. So imagine that, suppose that a class at SUNY Purchase contains all traditional college-age students and one retired person who is 75. The age of the retired person would be an outlier in this class. So everyone's like 18, 19, 20, and all of a sudden there's somebody in the room who's 75. The age of the retired person would be an outlier. Yes, that's right. Because it is significantly larger than the rest of the class. So I think you get the idea now. One number that's either larger, it could be small too. It doesn't have to be larger. But yeah, so that should do it. Now here I've got a numerical example of this. Here's a sample. And if you look at these elements carefully, what do you notice about them?
The 100 is really, really high, and the rest of it is
Yes, that's right. That 100 is an outlier. Now we're going to see what impact that has on the mean and the median. And this will help us understand, well, you'll see what I mean when we get to it. All right, so why don't we do two things? Let's calculate the sample mean, and then let's calculate the median. All right, so here's the mean. Now look what happened. Because of that one huge number, the average is 19. Now that's not a very good measure of central tendency. Why? Because it's larger than almost all the elements except for one, and it's much smaller than that outlier. So in this case, the mean is not very meaningful, is it? It's very heavily distorted. Okay, but on the other hand, let's look at the median. And the median, remember, we have to sort the numbers from low to high and then find the number in the middle. So let's do it. If you sort these out from low to high, you'll notice you have 6 elements, and just by coincidence, the 2 in the middle are both 3s. So clearly the median is 3. So I think you'll agree that in this case, 3 is a much more meaningful measure of the center of this data than 19. So the bottom line here is that the mean is distorted by outliers, while the median is not. In fact, if you look at this very carefully, This 100 could be any number. It could be 1,000, it could be 1,000,000, it could be 1,000,000,000, and yet the median is still 3. So therefore, we say that the mean is distorted by outliers, the median is not. Therefore, for data that contains at least one outlier, the median is a better choice than the mean as a measure of central tendency. Okay, although I would like to add to that, it turns out though, that if there aren't any outliers, then normally we use the mean instead. So we really only need the median when the data contains an outlier or outliers. So and we don't have, it goes a little beyond this class to explain why, but without outliers or with no outliers, the mean is a better choice because it has more convenient mathematical properties. And also, just for the simple reason, the mean, or it is intuitively easier people to intuitively understand the mean than the median. I mean, it's just the simple case that it's just easier to visualize what a mean is rather than a median. Many people have no understanding of what a median is, but everybody understands what a mean is. So most of the time we use the mean unless there's a good reason not to, which is the case of the outliers, and that's when we usually switch to the median. All right, so that's it for our discussion about mean and median. Now, I don't want to get too far ahead. I'm already getting a little ahead of my other class, so I'd like to stop right here, and we'll pick this up on Thursday, but don't forget, we also have to do the chapter 11 problem sets before we get back into this material. So on Thursday, we'll go over those problem sets where we're reviewing probability theory. And then if that doesn't take up the whole class, then we'll get back to this. All right. So in the meantime, I guess we'll call it a day, and I'll see you all on Thursday.
Can I talk to you after class, please?
Yes, you can.
It's pretty quick.
All right. Okay. So as soon as everyone else is gone, we'll do that.
Yeah.
Yeah, see you.
Thank you.
Bye. Thank you. Have a good day.
Bye.
Thank you.
Okay. Bye, everyone.
Okay, so I had a quick question about the midterm.
Yes.
I don't know if you can answer it or not, but so on the problem set, I was a bit confused because for compound interest, like it
Yes.
says like there's a formula A equals P
Correct. Yes.
parentheses 1 plus R over N, yada yada yada. But then it also says compound interest equals total interest
Oh,
minus
no, but
simple
that-
interest. So I
yes.
guess I'm a little confused.
Yes. The formula, that A formula is calculating the future value. Okay.
Right. Okay.
Then
That's
once you
kinda what I
have that, you can subtract the total interest. Subtract the principal to give you total interest. Then you subtract the simple interest, and what's left over is your compound interest. So that A formula,
Okay.
remember, is not calculating compound interest, it's calculating future value.
Okay. Gotcha.
Right? Is that all you needed to know?
And then I guess I had one more. I mean, I don't
Alright.
really know how to word it exactly. But so for questions where it's like annually and then semi-annually and so on, like for the answer, like the answer that I get for, let's say annually, would I take that answer and plug that in for semi-annually, or are they kind of unrelated? If you can answer
No,
that.
those frequencies only tell you what to do with the letter N in your formulas. So semi-annual means set N equal to 2. Annual means set N equal to 1.
I see. Okay.
That's all it means.
Yeah, that's kind of what I had in mind. I'm very cautious because like I did not do well in this class at all last semester. So I just wanted to be sure.
Really? You're taking it again?
I am, yes. So I'm
That's
very trying to be on top of things, you know?
Yeah, no, I seem to remember you did very well in the first midterm, so you're okay.
All right, great. Thank you so much.
All right, you're welcome.
All right, take care.
Okay, bye. Anyone
Bye.
else?
Yeah, quick question. The midterms due
Sure.
Tuesday, correct?
I think, yeah, Tuesday sounds right. Either, yeah, I think originally it was late Monday night, but
Yeah.
then I got delayed posting it, so I think Tuesday is fine too.
Okay, cool. Thank you.
All right. Anyone else? All right, then I'll see you all on Thursday.